Now we're going to look at a situation where we have what's called non-uniform circular motion. And we start off, the figure below represents the total acceleration of a particle moving clockwise, so this time it's going in this direction, in a circle of radius 2.5 meters at a given instant of time. The total acceleration is 15 meters per second squared. Okay, now something's different here. See, we have the velocity here, and when we've been dealing with centripetal acceleration, it has always pointed toward the center of the circle, which would be right here. This acceleration is not, and we need to talk about how that can possibly happen. So, now I'm back to something going counterclockwise again, but that's all right. If I have an object that's at this point at some instant, and it's traveling in a circle, there's the center of the circle, and it's got a speed v, the centripetal acceleration, and I'm going to have to start putting a subscript on that because it's not the only acceleration anymore. It'll point toward the center of the circle. If the object is moving with constant speed, that will be the only acceleration. And if it's over here, points toward the center from there, over here, points toward the center from there. But what if the object is speeding up or slowing down so that its speed is changing? If it's speeding up, it's going to have an acceleration in the same direction that it's moving, so it might have a component of acceleration in this direction. If it's slowing down, it might have a component of acceleration in this direction. And this acceleration at any given instant will be either in the same direction of the velocity or the exact opposite of the velocity. And so it is also tangent to the circle, and we call that acceleration, we'll use an a sub t here, but that acceleration will be tangential acceleration. It's always tangent to the circle. Now, here's some things about that tangential acceleration. It's always perpendicular to the centripetal acceleration, so now we'll have two components to the acceleration that are always perpendicular, but they're continually changing in direction. If this is something that's slowing down and it keeps slowing down at a constant rate, when the object gets over here, it'll have a centripetal acceleration in this direction, and perpendicular to that, it'll have a tangential acceleration in this direction. Now, the total acceleration is the vector sum of these two. Okay, so we could take this tangential acceleration here and slide it over, and the total acceleration would be this. And the total acceleration we'll just write as an A with an arrow on top of it. Now, what about calculating that tangential acceleration? Well, if you can use the language of calculus and derivatives, you can write it as the derivative of the magnitude of the velocity. Magnitude of velocity is just the speed, something like that, which you could write as dv dt without the vector stuff. You're just talking about the time rate of change of the magnitude of the velocity. Or, if you haven't quite gotten to derivatives yet, you could think of it as the limit as delta t goes toward 0 of delta v over delta t. And this v is just the magnitude of the velocity. Okay, so you can think of it that way. And that's what the tangential acceleration will be. So let's go back through the problem that we started with and take a look at this thing. Here's our total acceleration. We know that if that's the total acceleration, this object is going to have a centripetal acceleration in toward the center of the circle, and the tangential acceleration We could think of it as being out here on the tangent to the circle, but let's just bring it in here so we can draw the picture with the two. This would be the tangential acceleration right there. So let's see what we can figure out about these things. The first question asks, what is the centripetal acceleration? Well, I've got a right triangle here, 30-degree angle up here. The centripetal acceleration is the side adjacent to that thing. Side adjacent divided by the hypotenuse is the cosine of theta, or we're going to know, I'll write it down, but a sub c over a, hypotenuse is just a, is going to equal the cosine of 30 degrees, and they say somewhere here that we've got 2 sig figs, so I'm just going to make a note here, 2SF. By the way, when I'm grading things, if you see the symbol SF on there, that means your significant figures are astray. Anyway, the acceleration, the centripetal acceleration will be a cosine of 30 degrees to 2 significant figures. A is 15. It'll be 13 meters per second squared. The second question asks the speed of the particle. So here was part A. Part B is just going to be the speed of the particle. Well, a sub c is the one that's equal to v squared over r. So v will equal the square root of r a sub c. We have a 2.5 meter radius circle. Centripetal acceleration was 13 meters per second squared. Under the radical, I'll have meters times meters per second squared. That gives me meters squared per second squared. Square root of that is meters per second. That's good. Those are good units for a speed. I get 5.7 meters per second. So that's part B. C is asking for its tangential acceleration at that instant. Oh, I can just look at this little triangle here. The tangential acceleration divided by A will equal the sine of 30. Okay, so A sub r over A is the sine of 30 degrees, 2 significant figures again. And so A sub r equals, A happens to have a value of 15 meters per second squared. Oh, that's where it is. Sine of 30. I can do that in my head, right? The radial acceleration is going to be 7.5 meters per second squared. Okay. We probably won't have many problems where the angle's going to be 30 degrees quite precisely, but this one did happen to. Now, a challenge problem. I'm not going to do it, but see if you can figure out after how long will the particle experience 5 g's of total acceleration, and what will be the speed at that time. That would be how long after this instant. So that was our first introduction into non-uniform circular motion, where we have tangential acceleration. There's that sketch that we used to get that. Keep in mind now, the total acceleration is the vector sum of the tangential plus the centripetal. And remember, tangential and centripetal are always perpendicular to each other, like they are in this sketch. Here's a question regarding this that was an actual test question on a test that I gave a while back. I don't know how long ago. A flywheel in a factory has a radius of 0.975 meters. The flywheel begins turning from rest with an acceleration such that a point on the rim experiences a constant tangential acceleration of that. So I'll make a note to myself. The magnitude of the tangential acceleration is 1.05 meters per second squared. How long after rotation begins is it before a point on the rim of the flywheel experiences a radial centripetal acceleration of 1 g? Ooh boy. If it's experiencing a centripetal acceleration of 1 g, that means a sub c, which is v squared over r, is equal to 9.81 meters per second squared. Well, I can figure out what the v has to be at that time. I know the radius of this thing, and so I could say that v is going to equal, or v squared, I'll do it in 2 steps, is going to equal the radius times the centripetal acceleration, which in this case is 0. I guess I could just write it as 0.975 meters times this value of the centripetal acceleration, or v will equal the square root of that thing. So 0.975 meters times 9.81 meters per second squared. And I get v is equal to 3.09 meters per second. Now, here's the thing. This flywheel begins turning from rest, so the speed of a point on the rim, if it's got constant tangential acceleration, I can say that the speed of a point on the rim will equal v naught plus a tan, or at, that's what we're using, at times t. V plus at, but v naught is 0 when it starts from rest, so the speed is just going to equal the tangential acceleration times t. Well, we know the speed. We also know the tangential acceleration, so the time it'll take to reach that point will be v over the tangential acceleration, which is 3.09 meters per second divided by the 1.05 meters per second squared, and this ends up being about 2.95 seconds. At the instant described in part A, determine the magnitude of the total acceleration. Well, if we've got a circle here and the object is traveling in that circle, let's just suppose it's going clockwise this time, and it's got a tangential acceleration in the direction of the velocity, that's going to be 1.05 meters per second squared. And at this time, it's got a centripetal acceleration of 9.81 meters per second squared. The total acceleration, that's an A with a vector on it and no subscript. Well, the magnitude of A, this is just the Pythagorean theorem. These things are always perpendicular to each other. So magnitude of A is always going to equal the tangential acceleration squared magnitude plus the magnitude of the centripetal acceleration squared. So we just plug in the numbers here. And in this case, it's not that different from a g. It ends up being 9.87 meters per second squared. The centripetal acceleration is almost 10 times as much as the tangential acceleration, so that shows up when we calculate the total acceleration. So there are a couple of non-uniform circular motion problems.